Helicopters are truly remarkable flying machines. They can fly without a runway and can also descend vertically. They can hover in the air and move 360 degrees in any direction. This video delves into the hidden complexity and science behind helicopter flight. Once you understand the principles behind helicopter flight, you'll also see why the job of a helicopter pilot is incredibly complicated. Helicopters use the principle of airfoils to create flight. As the blades rotate in the air, the unique shape of the airfoil generates lift, allowing the helicopter to fly. The blades are powered by an engine, specifically a turboshaft engine. The compressor draws air in and compresses it. Fuel is then burned in this pressurized and hot air. The hot air that exits the combustion chamber passes through a series of turbine blades, causing them to rotate. There are two sets of turbines. One set powers the compressor, and the other set drives the rotor shaft of the helicopter. While jet engines in aircraft generate thrust, the primary function of a helicopter's jet engine is to rotate the rotor shaft engine. The most challenging aspect of flying a helicopter is controlling it. How does it fly forward? How does it fly backward? How does it fly sideways? Or how does it rotate? The answer is simple. Tilt the helicopter in the direction you want to go and fly. When the helicopter is tilted, the force generated by the blades is no longer vertical. 36% of this force propels the helicopter in the desired direction, while the majority of the force generated by the blades counteracts gravity. The real challenge is making the helicopter rotate along the desired path. To understand the science behind helicopter rotation, we need to delve deeper into the airfoil principle. The thrust generated by the airfoil, similar to an aircraft runway, changes with the angle of attack. Generally, a greater angle of attack results in more thrust. Now, imagine what would happen if one blade were at one angle and another blade at a different angle of attack. In this scenario, the thrust on the blades would differ, creating torque that rotates the helicopter. To ensure an equal distribution of thrust, the blades must continuously change their angle of attack to maintain a specific position. This complex process is made easier by the swash plate principle. Let's examine the exploded view and first understand its basic components. The lower swash plate does not rotate but can move and tilt as shown. The upper swash plate is mounted on a bearing on the lower swash plate, enabling it to receive the movement of the lower swash plate while rotating independently. The upper swash plate is connected to the rotor shaft by a drive, causing it to rotate with the blades. The blades are attached to the upper swash plate by control rods. Interestingly, by simply tilting the lower swash plate, we can change the angle of attack of the blades. This means that if the swash plate is tilted, we can maintain a positive angle of attack on the front side and a negative angle of attack towards the rear of the rotor disc. In short, the tilted swash plate generates torque. This type of control is called cyclic pitch. Now, let's return to the basic helicopter control. How does this torque affect the helicopter's movement? One might think that the helicopter will tilt forward and move forward. Unfortunately, this answer is completely incorrect. In reality, the helicopter will tilt sideways. As shown, this is definitely a strange effect. To rotate something, torque is applied in one direction and it starts rotating in another direction. This effect is called gyroscopic precession. Gyroscopic precession is not a new phenomenon in physics. If you look closely at Newton's second law of motion on a rotating object, you will be able to form a preconception of this phenomenon. According to Newton's second law of motion, the force is equal to the rate of change in angular momentum. Similarly, where's the change in torque angular momentum? Let's think about this rotating blade. As shown, it has an angular velocity. Now, assume that the helicopter has tilted due to some torque's action. If you subtract the second angular momentum from the first angular momentum, you will find the required torque for this motion. Interestingly, note that the torque applied to rotate the helicopter should be sideways. This means that the blade should be tilted sideways to tilt the helicopter forward. As shown, you can again see Newton's second law of motion at play. If you place the front part on the negative axis and the rear part on the positive axis, the helicopter will rotate sideways. Gyroscopic precession is actually an interesting phenomenon, but it perfectly confirms Newton's second law of motion. If you lift the lower airframe without tilting, the angular momentum of all three blades will change equally. This means that the lift force of the helicopter will be equal across all three blades, and the helicopter will be able to move up or down without tilting. This type of blade control is known as collective pitch. If you have ever seen a helicopter, then you must have definitely seen a tail rotor. Every rotor needs this tail rotor for the effective operation of the helicopter. Without the tail rotor, the helicopter's propeller becomes unstable in the same way as shown. This is the result of Newton's third law of motion. To understand this, let's focus on the longitudinal part of the force through the rotor. We know that the rotor gains angular momentum through a bevel gear, which is connected to the engine. The engine's bevel gear sends force to the rotor's bevel gear, as shown. But according to Newton's third law of motion, the rotor's bevel gear should send the force in the opposite direction through the engine's bevel gear. This reactive force will rotate the entire helicopter in the opposite direction of the blade. Along with the center of gravity of the helicopter, the tail rotor's job is to create a force on the tail and stop the helicopter from rotating in this way. The pilot can easily change the force generated by adjusting the pitch angles of the tail rotor blades. In this way, the helicopter can also rotate with the help of the tail rotor. The complex physics behind the operation of a helicopter means that flying a helicopter is actually a challenging task. Even a subtle change in the blade's pitch can make a significant difference in the behavior of the helicopter. Often, the pilot has to perform more than 2 operations at once to achieve the desired speed. Additionally, the helicopter does not react immediately to your input, so the pilot should have a good understanding of balance and equilibrium to operate the helicopter properly. Share this video with your friends and spread this knowledge. Thank you.